And we're back. Welcome back and happy Thursday. Today, we will continue on in a way with our discussion of confidence intervals, where last time we described what a confidence interval is. This time, we will describe how you calculate the confidence interval. All right. And so the material in the main text on confidence intervals will be section 9.2 through section 9.2.1, which is pages 247 through 249. Written exam number 2 will be roughly 2 weeks or a week and a half from today. It will start on the 13th of April and it will close on the 14th of April. It shouldn't take you more than about 1, maybe 2 hours, but given the circumstances, allow you flexibility in when you do the exam. This is to be an individual effort, and please make sure to sign and submit an honesty statement. So let's continue on. When we last left off, we talked about a confidence interval as being some interval AB. It's a so-called 1 minus alpha times 100% confidence interval for some unknown ground truth population parameter theta if that interval AB, closed interval, contains or covers that parameter with some probability or proportion 1 minus alpha. And so an example is if alpha is 0.05, we refer to 1 minus 0.05, which is 0.95 multiplied by 100, and that makes it a 95% confidence interval. So what does this mean? It means with some probability of 95%, theta will have values that are covered by that interval A and B 95% of the time. Well, that is almost like saying, not quite, but almost like saying 95% of the time you know the values. But what it's really saying is how sure are we that this unknown theta will fall somewhere within this interval AB. So it has a statement about the intervals that it's making, not about theta itself. All right. And so we talked about an example using the Poisson distribution, and we didn't know our ground truth lambda, so m many times. We took n many observations from some overhead camera, marking the arrival times of customers in a store, the entry box of a store. So for each interval, we take our samples and compute our estimator, calculate it, lambda hat, and so we have it for the 0th round, the 1st, the 2nd, up to and including the mth round to compute or calculate lambda m hat. And so because these are based on samples, and the samples are different from one another, from one round to the next, these lambda hats are going to be different from one another. And so we get a distribution, and this distribution, our so-called sampling distribution for lambda hat, it has a mean, and it has a standard deviation that we're calling the standard error to note that this is the distribution for a statistic and not for a simple measurement. And so we talked about the confidence interval probability as being this coverage probability associated with intervals, some proportion of the time. All right, so let's take a look at how we would construct these confidence intervals. So we have some sample, x1, x2, dot, 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 up to including xn. So we have little n many measurements, n is our sample size. And we want a particular confidence level that we'll call 1 minus alpha associated with whatever statistic we're going to compute. And so how to construct a confidence interval, we have some interval A, B, closed interval, so that includes the endpoints A and B. And this interval is going to satisfy the following relationship, that the probability that your unknown parameter theta falls within that interval A, B, is that probability is equal to 1 minus alpha. And so because we know we're talking about the probability that theta falls within some region, that's really going to involve a summation of probabilities for discrete probability, or an integral if it's a continuous probability over the set of values for the interval between A and B inclusive. And so let's assume we have an unbiased estimator. And as an unbiased estimator, we know it is a good replacement for this unknown ground truth parameter theta. And so one thing we can do for this estimator, let's assume that its distribution is normal, the sampling distribution of this theta hat. Now, as a normal, we can actually standardize it, and it doesn't really matter what distribution this theta hat is. And so let's take an example where we have two different distributions, and we have to examine the data governed by these two different distributions. On the left-hand side, we have the Poisson distribution with lambda 3, and on the right-hand side, we have the exponential distribution with lambda equal to 3. Now, of course, ground truth, you don't know what these lambdas are. I'm showing them to you, but in practice, for these population distributions, giving you values that you sample, x1, x2, up to and including x a little n, you don't really know what these lambdas are, but I'm showing them to you. And the Poisson, of course, is a discrete distribution trafficking in the number of events that arrive within standard modules of observation delta t. And exponential distribution is the amount of time that transpires between the occurrence of events. And this exponential distribution is a continuous distribution because it traffics in time, which is uncountably infinite. And so in order to make good comparative measurements between samples from these two distributions, right now we're making apples to oranges comparisons. So we want to make sure that these two distributions are cast in the same way so that we can make fair comparisons. So certainly the Central Limit Theorem tells us from last semester, stochastic computing, that we can make these two, this Poisson and this exponential, a normal distribution by ensuring that the statistic includes a sum. So you can add together things, those samples, and if those statistics, theta hat, include something that has a sum, it's going to look more and more like a normal. And so we have, let's call Sn, is the sum of n many measurements, xi, from each one of these distributions. So each xi could be a measurement from a Poisson, each xi could be a measurement from an exponential. And so if we were to take the expectation of this statistic involving a sum, and it doesn't matter if we multiply by a scalar or not, this is n times mu, and the variance of this sum is n times sigma squared. Now, of course, this results in a normal distribution regardless of the family of distribution, whether it's Poisson, exponential, gamma, uniform, what have you. It doesn't matter what they started out as. If our statistic, theta hat, includes a sum, the resulting statistic, its distribution, is going to be a normal with a mean equal to n mu, the expectation of that sum, and the variance equal to n times sigma squared, the variance of that sum. And so let's try this out in Matlab, and we're going to do this for the Poisson distribution, just to show you that normality is achieved just by computing a statistic that involves the sum. And so I will meet you in Matlab. So we're here in Matlab, and the first thing we're going to enterprise to do is to create a number of samples, and we're going to do that over a number of rounds. So let's start out. Num rounds is the number of times we're going to sample, and let's imagine these rounds. Let's say it's 1,000 rounds, and these rounds are going to represent the number of statistics we're going to report. Now, in the beginning, let's assume num samples. The first version is going to be 1,000 samples, and we're going to take this 1,000 samples and a Poisson with a lambda of 3, and we're going to sample from it. So my Poisson samples is equal to Pois RND with lambda, that's our parameter, and it's going to be 1 by num samples 1. So it's going to be 1,000 of these Poisson samples. Let me add in a little print. That's the style I like to follow, so I can set a breakpoint. So let's save, and let's let's run this. Num samples 1. Okay, little typo. So let's save this again, and let's run. So this is our set of Poisson samples. It's 1 by 1,000. And so I'm going to take this set of samples, and I'm going to plot that in a histogram. Num bins, and let's call that number of bins 20 many bins. All right, so now I'm going to type histogram, and I'm going to say give histogram for my p samples, number of Poisson samples, and let me name this figure, figure 1, and we're going to show what figure 1 is. And so if we do this, we take 1,000 samples of a Poisson, and let's increase the bin count. Instead of 20 bins, let's make it, how about 40 bins? So if we set that to 40 bins, let's save that and rerun it and take a look at our Poisson. So this is our Poisson. You'll notice it is not symmetric. Okay. So let's then take our number of rounds, and over some number of iterations, for I goes from 1 up to num rounds. So 1,000 many times, we're going to compute a set of samples and add them and show what the distribution is for that Sn. All right, so each round, let's say num samples 2, that's going to be the number of samples per round. Let's just call it 20. All right, so we have 20 samples per round, and we're going to say sample I is equal to Poisson R&D, lambda, the same lambda, 1 by num samples 2. So our sample size in this case is going to be 20, and we're going to say Sn is equal to, that's the sum of all of the samples on that ith iteration. So now we're going to save off all of these samples. Let's say the sample sums, or the sums, equal to zeros. We say 1 by num of rounds, because it's 1,000 times we're going to do this. We're going to save it away. So each time we compute the sum Sn, say the sums, the ith one is equal to Sn. So now that we save that away, let's create a new figure. We'll call that figure 2. In figure 2, we're going to compute a histogram of the sums, and we're going to show that histogram shape. So we quit debugging here, and almost forgot histogram. We forgot to put the number of bins. Num bins, and then for the histogram of the sums, num bins. All right, so let's save this and let's run it, and we'll see two figures. We see figure 1 and we see figure 2. Figure 1 has 20 bins. Let's try this with 10 bins instead of 20 bins, or maybe 15 bins. Oh, number of bins is 40. So let's bump that down to 20 bins instead of 40 bins. And let's rerun this. So figure 1, that's the Poisson with 20 bins. And you can kind of see the envelope. If we trace that, it goes up and down. But this other version, which is the sum of the Poisson samples, it almost looks like a normal. Let's see if we can bump up the number of samples in, or the rounds rather. So we say the rounds, let's call that 2,000. And let's say the number of samples 1, let's also call that 2,000, because we want the individual samples to be the same amount as the number of SNs. All right, so let's save that, and let's now run this and see what we get. Okay, so if we look at it, the envelope for Poisson, we see something that is skewed. It tails off to the right. And then for the version of the Poisson where we had the distribution of the Sn, we see that it looks kind of symmetric. And if we played with the bin count, of course, we would get something that didn't have gaps. So let's try that with the default 10 many bins. Let me quit, save, and let's just run this last version. So here we see figure 1, that's our original Poisson measurements. Figure 2, that is our distribution over the SNs, the sums of the Poissons. And you see here this distribution over the SNs, that looks very normal, like a Gaussian or normal distribution. And it is. And that plays out empirically precisely as we've been saying, theoretically, and it's due to the central limit theorem. Okay, so with that, let's meet you back in PowerPoint. So we just tried out this central limit theorem, and it says that if your estimator, your statistic, involves a sum, we can make it look like a normal distribution. And we just demonstrated that in Matlab. And so in order to make good comparative measurements between two different distributions, we need to take advantage of this central limit theorem and therefore not compute the raw measurements, but report some statistic over the raw measurements that includes a sum, because now something that's Poisson and something that's exponential would now look like a normal distribution. But the one caveat is they'll look like different normal distributions because the number of samples might be different, and if the number of samples are different, the terms in that SN, the normal distributions are going to be different relative to the original distributions from which those samples came. And so in order to make comparisons, which is what we want to do, that's why we cast these different distributions as normals. Let's imagine then we had two different distributions. We had 100 temperatures measured over 1 day, and a temperature is best described by a normal distribution. Temperature is an inertial physical quantity. And let's imagine we had 400 customer visits over 2 days. Customer visits, that's well described by Poisson, and that's be over 2 days. So by computing a statistic that includes a sum, we can get a different normal distribution with mean n1 mu1 and variance n1 sigma squared for the temperature measurements, and for the customer visit measurements, including that sum, we can get a different normal distribution with mean n2 mu2 and variance n2 sigma 2 squared. So now these two different phenomena, these two different systems, one is temperature and one is customer visit, temperature described by normal, customer visit described by Poisson. Now we can cast them both as normal distributions. Okay, but there's something wrong with this. What's wrong with this? Well, certainly n can be different, the number of terms in the sum Sn. The mean can be different, so n1 mu1 can be different from n2 mu2. Likewise, the standard deviation, therefore the variance, can be different. So n1 sigma 1 squared can be different from n2 sigma 2 squared. So not only can their centers be located differently, their dispersions can be different. So how exactly, even if they're normal, can we make a fair comparison between these two distributions? We can't. We can't make a fair comparison. And so what is the solution? Now recall when we talked about percentum, percentages, if you had a system that started out with a value of 200 and it went to a value of 300, and let's say you had another system that started out at a value of 100 and it went to a value of 150, we say that this one increased by 50% and this next one also increased by 50%. And in casting them down to what the equivalent would be per 100, per centum, centum being the Latin for 100, we can make a fair comparison that their rate of increase was the same, even though in the first system it increased by a positive 100, and in the second system it increased by a positive 50. Yes, their increases are different, but their proportionate per 100% increase is the same. And so our solution then is to put these two now cast in normal form distributions, our original Poisson, our original normal distribution on the left, and our Poisson distribution on the right, we want to now take their normal version afforded by Central Limit Theorem, these Sn sums. We want to put them on equals footing the same way that percentages did it for proportions or rates of increase. How do we do this? Okay, well, we start out with our two different normal versions or equivalents of our original distributions. For each measurement that we have, we're going to subtract the mean n1 mu1 and n2 mu2. That's for the normal version of it. So we're going to have here a distribution of SNs over temperature, and here we're going to have a distribution of SNs over customer arrivals. So now that we subtract the mean, the next thing that we do is we divide the result of subtracting the mean for each measurement. We take those results and we divide them by the standard deviation, which is just the square root of the variance. So in the case of the left-hand normal cast distribution, we divide each measurement then by sigma 1 times radical n1. And then for the second normal cast distribution, we divide each measurement resulting from subtracting the mean. We divide each one by sigma 2 times radical n2. And so once we do that, this takes our original normal distribution on the left and on the right, and it changes it to a special normal distribution whose mean is now 0, and its variance, and therefore its standard deviation, is now 1. Now this is called a standard normal distribution. Now, if we standardize or convert to the standard normal distribution on the left-hand side, we're also standardizing or converting to the standard normal distribution on the right-hand side. And so now in the standard normal form, we can make fair comparisons in the stochasticity between these two systems, even though they started out very differently. On the left, we started with a normal because temperature follows a normal distribution. On the right, we started with Poisson because arrival rates starts as Poisson distribution. And so now we can make comparisons. We can do things like ask, do they behave the same? What do we mean by behave the same? Do they spread similar amounts of probability mass over the same locations in the support set over which the distributions are defined? How much probability mass falls between the range of values, for example, in the interval from minus 0.5 to positive 0.5? You can make fair comparisons because now they are precisely the same distribution, the standard normal. And so here, let's take a look further at the standard normal distribution. Sometimes it's called the Z distribution. So Z distribution is nothing more than a normal distribution with a mean of 0 and a variance, and therefore a standard deviation of 1. Sometimes it's called a unit variance. Now, the standard normal distribution is a probability distribution, and as such, if you integrate from minus infinity to plus infinity over all the values in the support set for which the distribution is defined, we're going to get a total area under the curve of 1. The law of total probability tells us that. And so here, when we take our standard normal distribution, we have some values that we call the so-called Z values. And the Z values are members of the support set over which the standard normal distribution is defined. Now, there are some Z values that we will subscript with alpha over 2. And what this alpha over 2 subscripted on the Z value represents is that if we take the Z value for Z alpha over 2 on the negative side at a certain distance from 0, where 0 is the mean mu because it's the standard normal, and we take the Z value or that support set over which the distribution is defined, subscripted with positive alpha over 2 on the positive side of the mean, well, these values are such that the area under the curve for the left-hand tail, that's this part, and the right-hand tail, that's that part, the total probability for these two tail regions is alpha over 2. Now, of course, if you have alpha over 2 here and alpha over 2 area over here, alpha over 2 plus alpha over 2 is equal to alpha. So if these tails represent a total of alpha probability mass if you were to take the integral from the negative z value going to the left and the positive z value going to the right, and you add them up. That's exactly alpha. So what does that leave? Well, that leaves, because of law of total probability, in the center region, that leaves an area of 1 minus alpha under the probability curve. And so what that means is that if we take the area under the curve from the negative z sub alpha over 2 to the positive z sub alpha over 2, that's going to give us a total area under the probability curve of proportion 1 minus alpha. And so here, these z values represent quantiles associated with the amount of probability mass that we have integrating to the left and the right on the tails. And it's not just always the tails. You can have other z values closer into the interior. All right. So recall the p-quantile. And the p-quantile had a notation q sub p. And this is the value, i.e. member of the support set, the value over which the distribution is defined. This p-quantile, q sub p, is the value for which a proportion p of the probability mass or density is found. And so this minus z sub alpha over 2 z value is nothing more than the alpha over 2 quantile, and this other z value on the positive side of our mean mu, which is 0, is just the p-quantile associated with that value that leaves you alpha over 2, the probability mass, on the high side. And what is that? That's just 1, the total probability mass, minus alpha over 2. And so this other z value on the upper side, that z sub alpha over 2, the positive z value, that's just the 1 minus alpha over 2 quantile. And so here we have the alpha over 2 quantile. It's that value that represents alpha over 2 proportion of the probability mass. And then here, this other z value that represents 1 minus alpha over 2 of the probability mass. That entire area under the curve from minus infinity up to that z alpha over 2 value. And so this is relating the z values to quantiles. A z value is nothing more than a p-quantile associated specifically with the standard normal distribution, or the so-called z distribution. All right. And so we said our confidence interval is some range of values, a, b, that satisfies the probability mass within that interval equaling proportion 1 minus alpha. And so distributions, we said, can be made normal by summing, but that's not a fair comparison by involving some statistic over those measurements where that statistic has a sum. And so we normalize. We said for each measurement, we subtract the mean of that sum, and we divide by the standard deviation of that sum statistic. And that resulted in a standard normal distribution. And so we take our expression for what it means to be a 1 minus alpha % confidence interval. We set up that probability for that interval between A and B for our unknown population parameter being that proportion 1 minus alpha. And we're going to replace that with our estimator. Now, of course, what this represents is a kind of test to see how often this estimator for theta, we call it theta hat, falls within this region on the closed interval between A and B inclusive. And so the A and B endpoints are going to be the z-scores for the normalized version of the data, for which you used a sum and you subtracted the mean and divided by the standard deviation. And so as such, we're going to say, okay, well, we want to take our statistic, theta hat, that involves a sum, and we're going to subtract its expectation, and we're going to divide by its standard error. That's how you normalize a statistic. That statistic is assumed to involve a sum, and you subtract the mean. The mean of it is the expectation of theta hat, and we divide by the standard deviation. The standard deviation of theta hat is going to be the standard error. And so then we recast A as being that minus z over alpha of z sub alpha over 2. That's going to be our alpha over 2 quantile, right? Our p-quantile, p is equal to alpha over 2. And then here, this other z value, z sub alpha over 2, that's going to be our 1 minus alpha over 2 quantile for the z distribution. Now, of course, this exactly fits what it means to have all of the probability mass between these values is equal to 1 minus alpha, because to the left of this minus z value is going to be alpha over 2 proportion. To the right of this other z value, this positive z value, is going to be alpha over 2 proportion. Alpha over 2, that's alpha. What remains in the middle in that interval between the two z values, the minus z value and the positive z value, is going to be 1 minus alpha. And so we normalize our statistic theta hat in order to use these z values, the minus 1 and the positive 1, as the A and the B bounds defining the interval for your confidence interval. All right. So now we're going to do a little bit of algebra. We have an inequality. We have going from left to right, less than equal to, and we have a less than equal to. We're going to multiply both sides of the inequalities by the standard error of our theta hat. And we're also going to multiply the center value between the two inequalities by theta hat for a mathematically correct operation. So when we do that, that standard error of theta hat is going to go away because we have a copy in the numerator and in the denominator. And then we're going to have a theta hat multiplying this negative z value, and we're going to have a standard error of the theta hat multiplying this negative z value, and we're going to have our standard error of theta hat multiplying this positive z value. So if we do that, we have minus z value times standard error of theta hat less than equal to, or at most, theta hat minus theta, because it's minus theta because the expectation of theta hat is theta. And then we have at most less than equal to the positive z value times the standard error of theta hat. So now that we do this, we're going to make another operation. We're going to subtract theta hat from all of the sides of the inequality, from the center, from the left, and from the right. So let's do that. So if we subtract theta hat minus theta hat from the center, well, that's theta hat minus theta hat, that goes to 0. If we subtract theta hat from the left-hand side of the inequality, well, we have a minus theta hat down here. And then if we subtract theta hat from the right-hand side, we have a minus theta hat out here. And so now we're going to multiply all sides of the inequality by a negative 1. And when you multiply an inequality by negative 1, the inequality flips. So it's going to flip from less than equal to greater than equal to. So if we do that, okay, well, we have our minus theta, and now we're going to multiply. So if we multiply by minus 1 in the center, and minus 1 on the left, minus 1 on the right. If we multiply by minus 1 on the left, we have a positive theta hat, a positive z sub alpha, times our standard error of theta hat. We have greater than equal to, where it used to be less than equal to. So that's a consequence of multiplying by minus 1. And then we have our theta, right, where we used to have minus theta. And then we have greater than equal to, where we used to have less than equal to. And then we have theta hat minus z sub alpha over 2 times standard error of theta hat. Okay, and so now when we see this expression, we can actually take this expression that we had from before. We have theta plus z, our theta hat minus z. So we did that multiplication, we get this expression, and now we can rewrite this expression from right to left instead of left to right. If we read it from left to right, we say theta hat plus our z-score times the standard error, theta hat, greater than equal to theta greater than equal to theta hat minus z-score times standard error theta hat. Now we're going to read it the other direction, going in that direction. So we're going to write our theta hat minus the z-score times our standard error, and then we're going to read out less than equal to. So here's our less than equal to. Theta, we write our theta less than equal to. Here's our less than equal to. And we're going to say theta hat plus our z-score times our standard error of the theta hat. So we do this rewriting. It does not change it mathematically. And this is going to give us our expression. And so we have our probability that theta hat is minus our z-score, alpha over 2, times the standard error of theta hat, is at most theta, which is at most theta hat plus our z-score, for alpha over 2, times the standard error of theta hat. Now we notice here we have theta, but we have theta hat plus or minus that z-score. And so we're going to collapse that down into a single expression, and we say our theta is going to vary between theta hat minus our z-score times the standard error of theta hat. Between that, that's on the low side here, this is our theta hat minus our z alpha over 2 times standard error of theta hat, and it's going to vary between the low end plus, between the low end and the high end, that's going to be our theta hat plus our z-score, alpha over 2, times the standard error of theta hat. And so we say that theta is going to be in the interval which is identified by theta hat plus or minus our z alpha over 2, our z-score, times 1 standard error of our theta hat. And this is going to be our 1 minus alpha times 100% confidence interval, because if we take the area under the curve in this region, that's going to represent 1 minus alpha of the total probability. And so with a probability of 1 minus alpha times 100%, our ground truth, our unknown ground truth population parameter is covered by this interval A and B. Now, what is A and B? The A value is that theta hat minus z alpha over 2 times 1 standard error of theta hat, and the B value, which you calculate, is our theta hat plus our z-score, z alpha over 2 times 1 standard error of theta hat. And you can actually calculate these from your data, and for the z-scores, you can look that up from a table because it's the same standard normal. They're well known, and you can just look them up. The so-called z-scores, which are the p-quantiles associated with the standard normal distribution. Okay, so with that, that's all I had for today, and gives you the prescription for how you actually construct the confidence interval, and you do that from data. All right, so we will end there, and as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.